Okay, hello everyone. So my name is William, and I'm going to present a technique that I am developing in my PhD research. It's also related to search-based refactoring. So the title of my presentation is Design and Evaluation of a Technique for Refactoring Recommendation. So let's start with some concepts. So we are working with design problems which are the result of design decisions that negatively impact quality attributes, for example, modularity and extensibility. Uh, for detecting design problems, sorry, just a minute. Uh, sorry. So for detecting the design problems, we may use some symptoms, for example, code smells. And so such symptoms usually are automatically detected and they may indicate the existence of the design problems. So for removing the design problems, developers usually apply a technique that is refactoring, uh, which consists of micro transformations that are intended to improve the code design without changing its behavior. However, uh, there are a lot of challenges in deciding where and how to refactor. So the existing tools usually provide a lot of symptoms for the whole system, and it's difficult for the developer to prioritize in which code elements the refactoring should be conducted for achieving the better results. And also, there are another problem related to the policies that a system may have. For example, a system may have an intended architecture that, for example, will tell that you cannot have dependencies between some kind of components. And a system may also have other policies such as exception handling policies. So how can we conduct the refactorings without violating such policies? So the goal of my work is to propose a technique that helps to overcome such challenges. So my technique is called OrganicRef, and it's intended to provide refactoring recommendations for removing the design problems. First, we are focusing on three types of design problems, which are the concern overload, complex component, and scattered concern. Here I provide an overview of my technique. Here we have the output recommender. Sorry, the name is wrong here. It's OrganicRef recommender. So this is the main component of the technique, and it uses other components for providing the recommendations. So we start with the quality monitor, which will detect the metrics and symptoms, such as code smells, uh, and will provide such information for the recommender for finding the better recommendations. We also have a prioritization manager, which will receive input from the user regarding which, uh, for example, what are the most priority objectives in the for that specific user. So, for example, some users may prefer to have a recommendation that will provide a huge improvement in the design, and the user will not care about the number of refactorings. On the other hand, we may have a user that wants the minimum number of refactorings so that it will not have a lot of effects on the design. So different users may have different priorities. So the idea of this component is to help with this prioritization, and this information will be used later for prioritizing the proposed solutions of refactoring recommendation. We also have another component that's important here, which is the scope detector. The goal of this component is to help to reduce the search space for the recommendations. So instead of recommending refactorings for the whole system, the idea here is to focus on in a specific context that is important for the user. For example, a user may want to prioritize the code elements that were changed during a specific task. For example, the last task that he conducted, or the task that he is conducting at the moment. So the idea is to focus on those code elements, and this component will help uh, reducing this scope. And finally, we will have the refactoring generator, which is the component that will apply the search-based algorithms for generating the recommendations. And this component will depend on the policy monitor, which is a component in which the user can provide what are the policies of the system. For example, what is the intended architecture of the system, so that we can generate refactorings that will not violate such policies. So, summarizing, the goal of this technique is to recommend a sequence of refactorings that are able to improve the structural quality of a subset of code elements that are the elements that are in the scope, the selected scope, without violating the system policies. So now I will present some details of the technique. It's still under development, but I will present what we have developed so far. So let's start with the representation of the optimization problem. In this implementation, we are using a vector containing a sequence of refactorings, where each element in the sequence will contain a type of refactoring and what are the elements involved in this refactoring. For example, we may have a move method for the full method, where we will move this method from class A to class B, for example. So we'll have a lot of refactorings that will be stored in this vector. For generating the initial population, we are working with the combination of two strategies. The first one is inspired on the J deodorant tool. So we are using the heuristics for God class and feature envy. And also we have a second strategy that was developed in a previous works of our group, in which we extracted patterns of refactorings from multiple open source uh, Java projects. So we are using such patterns for also for the generation of the initial population. As we intend to test both local search and global search algorithms, we will need different strategies for generating the initial population. So for local search, we will generate only one initial solution that will be based on the combination of the two strategies that I mentioned earlier. And in the global search, we need multiple solutions in the initial population. So we will generate such solutions by using our two strategies and by combining them with, for example, the random selection of other refactorings for building our initial population. So besides the vector representation, we will have also a complementary representation, which is based on the EST from the Eclipse Java development tools. And the idea is to have a representation that we can manipulate and evaluate the fitness of our proposed solutions. So this representation will have all the code elements of a project, for example, classes, fields, methods, statements, and so on. So we are also working on the implementation of our operators. So for example, we are implementing some mutation operators where we, for example, may replace one refactoring from the vector with another one. For example, we may refactoring multiple multiple moving methods with a structured class, for example. So we are creating those such operators so we can use them during the evolution. We also are implementing crossover operators for combining the different solutions and generating new ones. Regarding the objective functions, we are still defining which ones we will use, but so far we have some candidates. The first one is reduce the number of symptoms, which is basically evaluate if a given solution will have less symptoms than a previous one, for example. And we have a related one, uh, which is intended to reduce the symptom diversity, which is the number of types of symptoms in the selected context. And also we have another metric which is related to metrics. The idea here is that in some case we may not be able to fully remove the symptoms, but we may be able to reduce their intensity. So we will evaluate this through the related metrics.
William, I have a question. About the diverse symptoms, it includes it's mere agglomerations?
No, it's somehow related to the idea of agglomerations, but I think it's not. How can I say? We are not using this concept of agglomeration. I think the idea of agglomeration is more related to the number of symptoms, the first objective.
Okay.
Okay. We also have another objective, which is very common in search-based refactoring techniques, which is to reduce the number of changes because some developers, as I mentioned earlier, may not want to conduct a lot of refactoring. So with this objective, we intend to provide the minimum number of operations for improving the quality of the design. And finally, we have a less candidate for objective function, which is the modularization of concerns. I forgot to mention when I was explaining the model, but we are also working on the use of existing techniques for automatically detecting which concerns are implemented in each code element. So the idea is to identify, for example, code elements that have a lot of concerns, and with the modularization of concerns operator, we intend to identify, for example, solutions that are able to better modularize the concerns, for example, removing multiple concerns from a overloaded element. We also need some constraints. The first one is that refactoring should not introduce other relevant symptoms. So the idea with this constraint is to not introduce other problems when removing a problem such as a concern overload. So we may introduce a lazy component when removing a concern overload. The idea of this concern is to avoid such situation. And also we have another constraint, which is that related to the refactoring policies. So here we are enforcing the idea that the recommended refactorings should not violate the policies of the system, such as, for example, create a dependence between components that should not exist, or expose an exception for a layer of the system that should not know about such exception. So this is what we have so far. We are still working on the implementation. Now we are working on the detection of concerns, also on the implementation of the policy constraints, and we are working on the implementation of the different algorithms that we will test in our solution. Uh, we also need to run an evaluation. So that's why I was asking about the existing tools for Mohammed. Uh, and the idea is to compare our proposed technique with the existing one, and uh, and then we can evaluate the quality of our technique. So that's it. Thank you.